Consortium, I'd like to thank you for joining the third installment of the IQ 3R's Reproducibility Webinar Series. This webinar is presented by the Reproducibility Working Group and is sponsored by the IQ 3R Translational Predictive Sciences and Statistics Leadership Group. Today's webinar is entitled Opportunities for Adaptive Design in the Preclinical Space, and our presenter is Dr. Yilin Chu of AbbVie.
Welcome everyone to the third webinar of this interesting series. So our guest speaker today is Dr. Yilin Chu. Yilin Chu is a Senior Director of Statistics at AbbVie. She is responsible for a global team of 40 statisticians to provide statistical supports for discovery and pharmacology studies across all therapeutic areas. During her 26-year career in the pharmaceutical industry, Yilin has pioneered and implemented many innovative designs and performed various analyses, including PK and PD data, efficacy, safety, QT studies, in vitro dissolution studies, pharmacogenomic
mice actually will live at least about 18 months. So one good thing about this is that we probably don't need a so-called vehicle or control group because without the toxin treatment, then the mice will live. But then we want to apply a toxicant to induce measurable phenotype that is some kind of fatal toxicity, and then which can be halted or reversed by our experimental therapy. So that's the objective. So to make it a little bit more concrete, the objective is to establish the so-called maximum tolerated dose of toxicant, which induce 30% mortality rate in mice. So that's a very clear objective a researcher have in mind. Then, what about the experimental design? So this is a very intuitive design, and it kind of makes sense, actually. So step one, perhaps we treat 6 mice, but at that stage when this proposal was made, scientists were not exactly sure what's the optimal number, but let's say treat 6 mice with some dose starting low of a toxicant for 5 days. If less than 30% of mortality occurred, and IACUC permits, according to animal welfare, then move to the next step. Otherwise, we stop. So then this is going up in a graduate escalation manner, and then every step we treat mice at a certain dose for 5 days, and then observe if we have approximately 2 out of 6 mice, right, died from the treatment, and then we can pretty much utilize that to identify the maximum tolerated dose. And then if it's less than 30%, then if it's permitted by IACUC, then we continue to go up. So there are 2 questions from researchers. So they approached us. The first question they have is very intuitive and is actually a very good one. So they asked, what's the sample size required for each dose group? Identify the MTD that lead to 30% fatality rate, right? So it's considered dose limiting. And they appreciate that a very small sample size is almost like a coin tossing, and the result may not be stable. And the second question is that, is there a better way to determine a set of candidate doses for the escalation? Let's address the first question. So this actually was also proposed by our scientists. So they asked us if we can provide some sort of sample size estimation for survival analysis, because after all, we are looking for 30% mortality rate, right? So, but then we did very simple calculation, and then we knew that it required a lot of assumptions in the calculation, but essentially we would need 80 plus, which is actually not that surprising. I mean, we all know that for survival analysis, in order to have that kind of a proper statistical power, you do need a lot of subjects. So 80 plus rats or mice, I'm sorry, yeah, to reach a statistical significance, that's certainly not quite feasible. And then the second question is also a very good one. So is there a better way to determine a set of candidate doses for the escalation? So scientists essentially propose something similar to modified Fibonacci sequence, right? Golden ratio. So from maybe 200, 400, 500, 600, and so. But there's a problem, what if actually the MTD, the maximum tolerated dose is 300, right? It's not among one of the pre-selected dose level. Or what if actually, to our surprise, the MTD is, say, 700 or 800, right? And then we wouldn't have an opportunity to interrogate that dose, or actually if we don't see much of a toxicity at these 4, and then animals are wasted, and then we probably have to amend the protocol and then add additional higher dose level. So as such, we propose an adaptive design. So adaptive design should be tailored for objective of each study. So for this particular study, we want to find the maximum tolerated dose that is dose limiting, right? So there's a quantitative way where we can graph the dose on the x-axis, and then the toxicity rate, right, in the y-axis. The worst will be 100%, and the best will be 0%, say untreated mice. Then and then we can kind of come up with a set of assumptions, and then we often call that toxicity skeletons. Then we can kind of draw those lines together. It gets estimated by researcher before the experiment. Those exercises need to be done sort of, regardless this is adaptive design or not. I would say actually it's even more important for the fixed design, because and then what kind of dose levels should we choose, right? Then normally this is monotonically increasing and distinct from each other and should be spread reasonably well apart. We certainly don't want to put a lot of mice in a very narrow dose range. Then that's probably not the best use of the experiment. But then an adaptive design will help us with the real-time data-informed design utilizing machine learning. So we can model a smooth dose response curve to fit the toxicity skeleton. And then we can apply a Bayesian two parameter logistic regression curve for modeling. And then for this particular presentation, I'm not going into details of other options. There are many options of different models. But essentially, two parameter logistic regression have worked very well, especially for a small data set. Then the target MTD, maximum tolerated dose, for this particular example, correspond to 30 percentile on the y-axis, right? That's what we want. So then the curve can help us project the MTD, which if you look at the x-axis, that corresponds to 30% toxicity rate. So an adaptive design can allocate the next cohort of animals to any reasonable dose, or most effectively, the estimated maximum tolerated dose based on a dose response curve. So it's a continuous learning, machine learning process. And then so I will demonstrate an example. So hopefully this will be easily understood without having much statistical notation. So the step one, okay, so we can, this is just an example. So we can treat 10 mice, I think conservatively at 210 microgram per kg. And then the result is that we observe one mice with a dose limiting toxicity, right? One death. And this is 1 out of 10. So obviously it's 10% in the y-axis. So it's pretty simple. X-axis, we have that corresponding dose level, and then the y-axis, the toxicity rate, right? So we just plot our data point there. It's 10%. And then the next step is that we can use the observed data to fit the dose response curve based on the outcome, right? Then after this first step, then the model can project or estimate a maximum tolerated dose as 388. But of course, we're not done yet. So the next step, let's say, since the model projected 388 microgram per kg as the optimal, or at that step as the maximum tolerated dose, it probably will be most efficient to treat all mice in that dose level. But let's say, so again, this is made up, but I'm hoping that this is also as realistic. Let's say I, cook, has a little bit concern and want to be a bit conservative. So then we decide to treat 3 mice at a lower dose level, 275. And then 3 mice at 388, which is the model projected maximum tolerated dose, right? Then let's say for some reason we don't observe any dose limiting toxicity. All mice survived. So these mice, again, we plot the actual data point on the graph. And then the model will take into account of all the accumulated data. So unlike the traditional design, which we move on, actually the data have been accumulated and then modeled accordingly. So now, as we can see, based on this new information, the model projects the MTD to be 672 microgram per kg, pretty high dose. Then the next step, so we decide to be aggressive. Let's treat 3 mice at 692 microgram per kg. Then we observe 2 mortality, 2 deaths with the dose limiting toxicity. So that's a 67%, right, on the y-axis. That's our data point. So we continue to update the curve based on all the accumulated information. So this is really truly a dynamic design with memory. The model now projects the MTD as approximately 600 microgram per kg. Then step 4, since that dose is what we have estimated or identified from the previous step as the maximum tolerated dose, so we treat additional 3 mice at that dose level. Then we see 1 out of 3 with dose limiting toxicity, right? So we plot that on the graph and then we fit the model. Then the model now projects the MTD as 587. So we can declare model convergence simply because this curve superimposes the previous curve. And then, or we can set up some sort of criteria. For example, 587 microgram per kg is within 5% margin of error of the previous estimated MTD. Then we can actually conclude that the maximum tolerated dose for this toxicant is 587 microgram per kg. So that wrap up the process. So just to make the curve fitting a little bit more clear, this is sort of an animation, again, repeating the previous step, but then you can see clearly how the model shift according to the data, right? So the first step, we have 10 mice, and then this is the curve from the first step, right? And then this is the first estimation. Then the second step, we have 6 additional mice. And then this is the second step where you can see that the data push the curve to the right quite far. And then we can see a new estimated maximum tolerated dose. And then add 3 more mice, then we see the data point, right? That push the curve or adjust it a little bit to the left. And then step 4, additional 3 more mice. Then we can see that the next step, the curve is pretty much superimposable to the previous step, right? So then that gives us a convergence. So again, this is just an example. Numbers are made up, but this is we can interrogate operating characteristic about the design and compare with the fixed design. So in this particular example, we are forcing the fixed design to go through all these 4 dose groups, right? But then in reality, actually, the design can stop prematurely, if actually we observe quite a bit of a toxicity at the beginning, or actually find no MTD, just simply because of the, kind of a point tossing random process, right? And then so then we can see that the sample size allocation for the fixed design pretty much not flexible, and if it goes well, then it will be as expected as what we have designed. Where the adapted design, we will see that we try to allocate mice so that we can most efficiently use those mice, so they are not being used in vain, right? So we try to allocate those mice at the what we think at each step, the maximum tolerated dose, to kind of increase the credibility of our estimate. So it doesn't really have to be fixed and then with an equal allocation, where we can use those mice more efficiently for animal welfare purpose. And then furthermore, actually, this is a comparison between the fixed design and continuous reassessment. The fixed design, pretty much we plan for 24, right? Continuous reassessment, it's really flexible. In this particular example, we use 22. But someone can argue maybe the first step, the 10 mice, may not be the most optimal way of assigning that many mice in that cohort. But actually, they are not entirely wasted because every single data point have been taken into account in the modeling. Now, that's the beauty of the continuous reassessment method. And then as previously addressed, using the fixed design, it will be among one of the pre-selected dose levels. And then when we see or observe 2 out of 6 mice with dose-limiting toxicity, or actually we could, the design could require additional protocol amendment if MTD is not reached. And then continuous reassessment will give you a pretty good estimate. And then, I think there probably will be a question now in everybody's mind that how precise that the accuracy or precision of this estimate, right? So I will address that question in the next segment. So the pros and cons, certainly fixed design, it's more straightforward. And then, but it need to pre-select those, but that also means it's pretty transparent. And then for preparing for the dose, it's also a little bit easier, right? And then, but the risk is not being able to identify MTD or declaring a lower dose because of a chance finding, or maybe actually MTD is not among any one of those pre-selected dose. And then a biggest problem in my mind is actually it may not be reproducible. So, the probability calculation is a little bit more complex, but to help people understand, you can think that if we use 24 mice, right, in this design, sort of like a 24 coin tossing process. How likely would you toss a coin 24 times, right? And then the next time you want to reproduce the exact same sequence, and then even the same outcome, it's virtually impossible. It's less than 1 in 10 million. So it's just virtually impossible to reproduce that. And then where the continuous reassessment method, we have the real-time assessment, and then it's flexible going up or down. Actually, it doesn't have to always go up. It depends on the model prediction, right? And then sometimes it can escalate a little bit too aggressively. But normally we will have IACUC, animal welfare, or if this is done in human, then certainly we have the board, ethics board that can actually cap the dose, so then we don't have to escalate too aggressively. And then it has a very reasonable precision in estimating the MTD. Even without a formal statistical calculation, as we know for the fixed design, we only have 6 mice that can offer us some understanding of the dose-limiting toxicity for each dose level, right? So then 6 is a small number. But then continuous reassessment method incorporate all the information into the modeling. So obviously it's a lot more precise. And then this is also a learning mindset rather than a fixed mindset. So again, utilizing the same example, but this part is a little bit more advanced. So if you are interested, please listen because then it also address some machine learning aspect. But again, I would minimize. There's really not much a statistical or mathematical notation, but hopefully this will help people understand what's really going on. Actually, the art is more of a behind the scene for machine learning. So in this particular example, in the beginning, we don't know which dose will be the maximum tolerated dose. So naturally, we can choose a so-called uniform prior. Basically, if we can classify our dose into, say, for example, 20 levels, categorize them, and then that means in the beginning, without much information, each dose can be a candidate for maximum tolerated dose, right? So if we have 20 candidates, then it's pretty flat. It's just 5% for each dose because we have no idea which one is the MTD. So that's it's actually a pretty reasonable assumption to begin with. And then in the Bayesian context, we call this a flat or uniform prior. So that's what it means. Then when we treat 10 mice at 210 microgram per kg, we observe 1, and then we fit the data, right? So not only the fit, the model give us the projected or estimate MTD as a 388. Actually, the beauty of the Bayesian, so I know that Tony will go much deeper next time. I'm really looking forward to his presentation regarding Bayesian analysis. And then, but the way how Bayesian operate is to integrate the data, right? I use the red color for data. Then also the prior, that's the green part, and then come up with the so-called posterior probability. So after that kind of a marriage, then we can actually look at the so-called posterior probability. So instead of being flat, now you can see that it start to kind of peak up. And then you can see that obviously around 400 microgram per kg, that's more likely to give you, more likely to be the maximum tolerated dose, right? So, so the purple part after the integration of data, so in Bayesian context is called likelihood, and then the prior, then we come up with a posterior probability, right? Then a very famous statement in machine learning is that the learning strategy is that yesterday's posterior is today's prior. So as you can see, the purple bars become green now, preparing for the next step. And then in this next step, we have a more informative prior, right? So in this particular step. So again, we treat 3 mice at this 275, and then 3 more mice at 388. This is a result, and then we push the curve to quite far right. Then the model project the MTD as approximately 700 microgram per kg, right? But the thing is, actually, there's an artifact behind the scene, not only monitoring the projected MTD, but then also the posterior probability, because then it shifts a little bit to the right, but it's a bit flat because it kind of get a not very consistent result from the previous step, right? Then the next step, then again, yesterday's posterior is today's prior. We treat 3 more mice at 700 microgram per kg, observe 2, and then we project the new MTD as about 600 microgram per kg. Then we can see that the bar is getting, more concentrated, and then ideally, if you can see that become more and more concentrated, and then you know that you're pretty much very close to the, hopefully the truth, right? So then step 4, so again, yesterday's posterior is today's prior. Then they become green, and then we treat 3 more mice at the 596 microgram per kg. We observe 1 with DLT, and then so we can declare model convergence, and then there can be different criteria, but a Bayesian criteria is actually look at the posterior probability to see, those bars. If you think they are concentrated enough, that give a quite a bit of a good credibility in terms of this maximum tolerated dose estimation, right? So this is the really the cool part of machine learning, where actually behind the scene what's really going on, and the model is being programmed in a way that the model is forced to learn, forced to go back and forth, as you can see, that the data push the model to the right and push it to the left. So what I want to say is that, at this step, for example, the curve might look a bit ridiculous because it's still in the learning process, So in the current world, now we have a lot of machine learning and artificial intelligence. Sometimes you see a very strange or even stupid, result coming out from the tool. But actually, that's only part of the learning process, because an architect is actually behind the scene monitoring the posterior probability. And guess what? Those actually only about 2 steps away, or 3 to 6 miles away from going to the convergence, right? So it's actually a little bit scary in a sense. So I want to say that if you truly understand machine learning, please do not underestimate. So for example, say ChatGPT from OpenAI, right? So sometimes they give very strange answers to your question. I suspect, or actually, I even want to say I believe that's intentional, because it's a part of a learning process. And then maybe the curve look very odd, or the projection look very inaccurate, but it could be actually just few steps away from convergence. So so in conclusion, what I want to say is not all new technologies will be better, but some have been tested and proven to be more advanced, right? So I kind of use a metaphor from climbing the stairs or versus taking an elevator. The initial icon had certainly humans in the elevator, but I replaced humans by a mouse. So just to fit into the context of this presentation. So in a nutshell, compared to the fixed design, continuous reassessment adapted design, CRM, provides estimated MTD values that are both more accurate, that means estimated MTDs closer to the target, and more precise, smaller error bars for estimated MTD. And then, so we look forward for active collaboration in study design, because it needs to be fit for purpose. And, if machine can learn, we need to have a adaptation, and we really truly need a growth mindset. So that pretty much conclude my presentation. And then I would like to acknowledge IQ Consortium, and then also our statistician in our department for bringing up the research problem to our attention and working on the actual project. So thank you.
Thank you, Yiling, for the great presentation. So any questions from the audience?
Yeah, I see a raised hand.
I would like to remind everyone to please write your questions into the Q&A module, which you would find by selecting the ellipses at the bottom right corner of your screen, and then selecting Q&A and typing your questions there.
So while you are writing your questions, maybe I can jumpstart the process by asking a question of myself. So I'm just wondering, because we are seeing these continuous steps, so I'm just wondering whether there's a general guideline on when to stop further testing steps, basically saying that it's converged.
Yeah, that's certainly a very pragmatic question. So we have an understanding that this is often based on feasibility and animal welfare. So the goal is not to be excessive, right? And then, but normally for the convergence, we can have a quantitative decision. So either before the design, we can run simulations for different scenarios, and then look at the maybe agreed upon quantitative design, how the posterior distribution will reach a certain point where you have a high credibility rather than that initial flat stage, right? Or actually alternatively, if it's more for exploratory purpose, we can designate a feasible number of animals, and then none of them will be wasted anyway. So as they accumulate, and then we model the result, calculate the posterior distribution. And then, we know that, even if we say, okay, it's time to stop because of the operational consideration, which is fine. And then, but we have a pretty good sense of the credibility, right? Maybe it's reached 80%, or maybe 60%, or maybe it's only 30% for some reason. Then we know that we probably need to have more animals to draw meaningful conclusion. Or, even if we cannot, then we know that there's still, is a quantified uncertainty that we know that we are not there yet. But normally, CRM work pretty well, even for a very small data set from our experience. We started running this type of design in first in human design for oncology, starting from 2005. So that's almost 20 years ago. And then it has been proven that this can get us treat patients more efficiently and identify those where we can have this kind of understanding of toxicity, which is important. I see a few raised hand. I don't know, if there's a way that we can address the question, or.
We'd like to take all of the questions using the question module. So if, rather than taking folks off mute, so please do enter your questions in the question module by typing them in. You'll again find them at the module at the bottom right corner using the ellipses and selecting Q&A.
Right. Yeah. Sorry, I was on mute. Yeah, I was saying thank you so much for the answer. We do have quite a few questions coming in from the Q&A module. So I'll just read from the beginning. So the first question is that, is it likely that the method you suggest will usually result in fewer mice needed? Or is it likely that maybe more may be needed depending on the compound?
Yeah, so things are relative. I would say compared to the fixed design, based on our own empirical, actually the real experience, also simulation. Certainly we run tons of simulations. It will result in fewer animals for sure. To have that kind of understanding for maximum tolerated dose.
I see. The next question is that I'm wondering how the posterior distribution is incorporated into the CRM process. Is a Bayesian regression model used?
Yes, it's a Bayesian model. So for the model itself, it's pretty simple. It's kind of like regression model. It's not linear, but it's a very simple 2-parameter logistic regression in this particular case. So the posterior probability will be calculated by the Bayes theorem. And then this particular example, you even have the actual analytical solution, but depending on how you set that up. But then so as we know in all regression model, you not only have a point estimate, say for your slope or your predicted value, but then you can also obtain that kind of a precision estimate behind the scene, right? So in Bayesian context, because it's not just data driven, but it continue to incorporate the prior knowledge. So it's not called confidence interval, but it's called credible interval. But basically it characterizes that precision of your estimate. So you can see that precision is increasing and increasing as your data accumulate, and then the credible interval get narrower and narrower and narrower. So we can also provide a credible interval, say 90% credible interval for an estimated MTD, projected MTD, and then you can see if that's narrow enough for you to call for a stop.
So the next question is that in classical logistic regression, you run two issues if all responses are 0, meaning no DLTs. So is this an issue in the case of the Bayesian logistic regression? But I assume not because of the prior, but what is the next step if you see 0 DLTs at the initial dose? Do we go to a second predefined dose?
Yeah, so the simple answer is yes. There are a lot of sophistication, behind the scene, and then I can say actually in a lot of in practice, we don't even need uniform prior. I mean, people have some sort of idea, or from publication or some idea, or maybe it's tested in other kind of rodent, and so have some sort of idea. And then so basically the model, if you see even 0 to begin with, actually that's not uncommon for human. That's pretty common because we want to start very low, especially in first in human study. So that means the model would take you up, so it would say we're really not there, especially if you treat, say, 10 subjects and then you see nothing, and then the model will ask you to go up quite a bit. But again, I cook or the ethics committee can say, okay, let's still try to be careful and then, escalate a little bit more slowly. So yeah, it's very, very flexible. But the model itself basically will ask you to go up.
So what kind of software is needed to complete an analysis like this? Is this something just the statistician in your group have, or do the toxicologists also have access?
I believe so. So I know that, for example, MD Anderson, they mostly target for first in human studies, but they have some free software for downloading. There is a software called Find. I think it's actually specific to CRM, and there are other algorithms out there as well, right? So this is truly one particular example. But yeah, there are definitely software to download for CRM or other adaptive design.
It seems like time is the biggest drawback to an adaptive approach. Is there anything that can be done to get results faster?
Yes, if we want to get it faster, then we'll be a little bit more aggressive, right? I would sort of argue that the time spent would be very comparable to the fixed design anyway, right? Because for fixed design, you treat 6 mice and then you wait for the result, and then you make a decision whether you will go up to the next step. So, pretty much also 4 steps in this particular example. So I would say, adaptive design is actually a lot more flexible, and then, it's a learning mindset. You incorporate everything, so you accumulate a lot more knowledge in the adaptive design. So yeah, I wouldn't say it would take longer. Actually, in our experience in first in human design, it's faster because it's more aggressive. So if we go by the traditional Fibonacci sequence, it's slower. But if we kind of trust the model, and then, or if we have actually good prior, then it can go up pretty quickly. I remember the team got really excited. Actually, the model tell us to increase, say, 300, 400 milligram increment, and then, but yeah, I mean, it works.
So the next question is somewhat related. It's asking any rationale determine the next exact dose in CRM, and will CRM be used to determine the therapeutic dose? And it seems that CRM will take more time determining the dose, right? So yeah, somewhat related.
Right. So obviously we can use CRM for efficacy too. So this example is to predict something with a toxicity rate. But then certainly we can use CRM to predict efficacy, or even a combination where it's a little bit higher dimensional rather than a curve. You have a dose response basically surface. But the more complicated objective you have, perhaps you need a little bit more subject. But it's definitely more flexible. And then also I want to say this particular example, we aim at 30%. It doesn't have to be 30%. You can aim at the whichever number you think makes sense for your own research, like 50% mortality rate or some sort of efficacy. So again, I really don't think it's lower. Actually, in our human trial, it's way faster.
So this is the follow-up question to the previous Bayesian question. So the question is how the final posterior distribution of the MTD will be used to make a final decision.
Yeah, without going into too much of a technical detail, but as you can see that the posterior distribution from the initial very flat curve and keep on converging, right? So at when during the learning process, it kind of shift a little bit, but then overall trend is that it keep converging and converging. So yeah, you can set up a criteria, say, the highest, the tallest bar, you want that to be more than 50%, 60%, or 80%, then you stop. So the higher the bar, then that means the more credible the result will be. Hopefully this addressed the question.
Right, yeah. So is there any concern with the use of the two-parameter logistic for predicting the 30% response regarding the high end of the dose range because of the implicit symmetry in the curve?
Yeah, that's right. Yeah, that's right. So it need to be tailored, so from our experience, a two-parameter logistic model work very well in many different scenarios because actually the curve can be bent. As you can see, it can be bent in different ways pretty easily. And then as long as your goal perhaps is not estimating a dose limiting toxicity, let's say at 90% at the high end, which is actually a lot more unstable, right? Because there's really not much room we can stretch at that part. Then, if something that along the line between 20% to say 70%, the model will work. But in simulations or at the study design stage, we can certainly consider other model. I know that some other pharma, they have tried a more aggressive power model, but it's a bit too more aggressive. So even when they see, say, 4 out of 6 subjects who experience a maximum tolerated dose, and then the model still tell them to go up. So I think, two-parameter logistic is kind of more flexible, and then it provide a good balance in general. But yes, obviously we should select, we think, the best possible model to address that toxicity skeleton.
Yeah, so the next question is also about the whether a traditional approach takes more time or the CRM takes more time. I think you've already addressed this. It looks like a lot of people are interested in the actual time needed
Yes.
for the CRM model.
Yes.
Yeah, so the next question is that in your example, when you choose the next group of animals to dose it, it seems that you did it all at once, meaning for the next 3 animals, you dose them at the same, you dose all of them at once. So potentially you could dose 1 animal at a time in order to try to save animal lives. Did you consider that, or are people not willing to wait that long?
Yeah, we can certainly dose animal one by one if there's a special animal welfare consideration, right? Because and then the cool thing about Bayesian is sort of like if you do 6 animal one by one, you can model, you can model after you get 1 data point, and then that certainly will be yes or no, yes or no, whether the animal have toxicity, but you can model. And then, but then once you accumulate 6, you model 6 times. Basically, it will be the same as you accumulate 6 altogether. Then you model them all together in the Bayesian context. So, I mean, from the statistical point of view, it's more of an animal welfare or operational consideration. But the model itself, you can do it either way.
So do you account for the uncertainty in the MTD estimate, for example, credible interval, when making a dose escalation decision?
So for the decision alone, we we recommend using the estimated MTD, which is certainly the center of the credible interval, right? But then it's not necessarily has a very good credibility, especially at the initial stage, right? So, but then as model continue to learn, then even not a statistician, actually now you guys know that it become more and more credible.
So in terms of adjusting animal numbers during a study, some people claim that we should add until we reach the result we want. Can you comment on that?
Add the number until so I mean, if you have ever worked with statistician, you know that we sort of always recommend the more the better, right? So, and then that's I mean, there's no free lunch, but this is need to be carefully designed and calculated behind the scene, right? And then we try to incorporate and utilize all the information we have in the analysis. So I mean, essentially, if you want better precision, then you certainly want more animals, and then it's going to be actually a very good discussion between a researcher and statistician, because then say if you want to gamble, right, you actually would like to have a little bit understanding of your odds, right? And then so we as statistician can tell you the odds, and then so you can decide whether you want to gamble and then what's your odds of winning. So hopefully this also addressed the question.
So the last question in the sequence currently is that for the traditional strategy, do you dose all the mice at once at all of the fixed doses?
So normally, because of animal welfare, so normally this type of design, even in a traditional sense, I believe that they dose a small cohort of animal per dose and then carefully escalate after that. So there are different kind of design, and I really looking forward to presentation from Tony. Definitely there are a lot of other considerations, and then that would fit for your purpose and then fit for what you are looking for.
Oh, we have a new question here. So do we need to repeat to confirm the CIM results?
I'm sorry, repeat to?
Repeat to confirm the CIM results. So basically, is a new study needed?
Sure. So I think it's probably related to reproducibility, right? So as mentioned that for coin tossing alone, it's very difficult to reproduce. If you imagine you toss a coin 24 times, right, and the next time you'll come up with the same sequence, it would virtually be impossible. But for the CIM, since it's using the data cumulatively, so if you reproduce, depending on if you choose exact same dose, I would say you will get probably, because of the random effect, right? So you will still get slightly different result per your cohort. So maybe say the first 10 mice, and then you get 0 toxicity. That's certainly very, very possible. But then the thing is that you accumulate the data and then fit a curve for that. And then so in the end, per our simulations, we can run 1,000 simulations, right? So simulation results demonstrated that the result could be quite consistent. So I don't have the opportunity to show all the details, but you can see, for example, if you run 10,000 simulations, and then the range of the MTDs, coming out from the CRM, and then it's pretty tight versus the traditional fixed design. The range of estimated MTD is actually pretty wide, because and then it's just simply it's very difficult to reproduce.
Okay, yeah, that's all the questions we have.
For joining us for this third installment of our 6th webinar series. I hope you are all able to join us for the next webinar. And if you have any questions related to this webinar after we close up here, please feel free to send them to me and I'll forward them along to our speakers and moderator. Thank you all very much once again, and we look forward to seeing you at the next session. Take care.
Thank you.
Thank you.
Bye.
Bye.